Okay, let's kick off this explainer by imagining something I think we can all relate to, being totally, hopelessly stuck in a maze. Whether it's a massive corn maze in the fall or just trying to find the exit at your local IKEA, you know for a fact there's an exit, but the path to get there? Yeah, not so obvious. So how do you find your way out without just wandering around aimlessly? Well, in computer science, we actually have a highly structured, incredibly powerful method for exactly this kind of problem. Today, we're diving into a brief introduction to the backtracking algorithm, and we're going to see how it helps you systematically navigate an absolute maze of possibilities.
Here is a quick look at our roadmap for today. 1. Stuck in a maze. 2. The state space tree. 3. Coding the backtracking algorithm. 4. Analyzing time complexity. And 5. When to use backtracking. Let's jump right in.
Section 1. Stuck in a maze?
All right. Imagine you're standing right at your first intersection in this maze. You know that one of the 3 routes ahead of you, A, B, or C, definitely leads to the exit, but you have absolutely no idea which one it is. To find your way out, you decide to play it smart, right? You gotta be methodical. You decide to test each option one by one, starting from the left by walking down passage A.
So you're walking through passage A, but you don't find the exit right away. Instead, you bump into a brand new intersection, and this one has 2 more routes, D and E. Your problem actually just got a little bigger, but you stick to your strategy. You're at a new decision point, so you make another choice. You try option D. You walk down the path, and boom, you hit a solid brick wall, a total dead end. But listen, this is exactly where the magic happens. You don't just stand there staring at the wall, you turn around, retrace your steps, and walk right back to that second intersection. This physical act of reversing your path when a choice turns out to be invalid, that is the very heart of backtracking. Okay, so having returned to the second intersection, you figure, let's try option E. But, yep, it also leads straight to a dead end. So you gotta turn around again, you return to the second junction. Now, you've completely exhausted all your options here. You logically conclude that neither path D nor E works, which means path A itself is a failure. You turn around once more, retracing your steps all the way back to your very starting point, intersection 1.
Having completely ruled out path A and every single thing connected to it, you confidently move on to path B. And success! You finally discover your way out. The crucial takeaway here is this. This brute force process of testing all possible paths, and most importantly, returning upon failure to try the next available option, is exactly what we call backtracking. You make a choice, follow it to its logical conclusion, and if it fails, you literally step back and try another.
Moving on to section 2, the state space tree.
Let's map this out. Every physical decision point in our maze actually maps perfectly to what computer scientists like to call a state space tree, or a decision tree. Intersection 1 sits at the very top. The choices A, B, and C, they branch downwards from it. Choice A leads to intersection 2, which then branches further into D and E. What was once this really confusing physical space is now a highly organized conceptual tree built just by mapping out every possible decision. Let's quickly break down the anatomy of this tree. First up is the root node. That's your initial state, kind of like standing at the maze entrance. The lines connecting all the points are called edges, and they represent the actual moves you make. The points in the middle are intermediate nodes, basically your partially completed states. Down at the very bottom are the leaf nodes, representing the end of the line, which is either a valid exit or an invalid dead end. And finally, a path is really just the sequence of decisions starting from the root and going down to a leaf. Visualizing this whole solution space is absolutely critical for figuring out how our code is actually going to traverse it.
Which brings us to section 3, coding the backtracking algorithm.
Traversing this state space tree is typically done using recursive depth-first search, commonly known as DFS. The core logic operates in a continuous 3-step loop. Step 1, you iterate through the possible decisions, you pick one, make it, and update your current state. Step 2, you recursively explore all paths branching from that newly updated state. Basically, you keep digging deeper. But Step 3 is the most important one. If that path doesn't work out, you backtrack. You do this by explicitly undoing the decision you just made and reverting your state back to exactly what it was before. Here is how that conceptual logic translates into a bare-bones Python template. Notice at the very top, we first define a termination condition. We literally have to tell the computer when a path should end, whether we've successfully found the exit or smashed into a wall. If we haven't terminated, we drop into our loop.
For every possible decision, we call a function to make that decision. Then we call our depth-first search function recursively to dig deeper into that path. And right after that recursive call comes the magic line, undo decision. That right there is the computer literally turning around in the maze, resetting its state so the next iteration can start totally fresh.
Let's jump into Section 4, Analyzing Time Complexity. To really wrap our heads around the efficiency or time complexity of backtracking, we need to look at two specific metrics within our state space tree. First is the branching factor, which we represent with the letter B. This is the maximum number of children each node has. Simply put, what's the most decisions you could possibly make at any given intersection? Second is the depth, represented by the letter D. This is the length of the deepest path in the entire tree, corresponding to the total number of steps required to reach a complete solution.
So, the really crucial point here is how these two factors combine. In a backtracking algorithm, the worst-case scenario means we don't find the exit until the very last path we check. We end up exploring every single node at every single level of the tree. The time complexity for this is estimated as big O of the branching factor times the depth, or O of B times D. Because it's essentially a brute force approach, the computational weight grows significantly as the maze gets larger and more complex.
Finally, let's cover Section 5, when to use backtracking. You know, backtracking isn't really meant for simple, straightforward problems. It is incredibly useful, however, when your objective absolutely requires you to explore or identify all possible solutions. If you need to generate every possible subset of data, calculate complex permutations, or identify all combinations, well, backtracking is exactly what you need. It is an exhaustive search method that guarantees, for sure, that absolutely no stone is left unturned.
By visualizing our options as a tree and methodically making, exploring, and then undoing our decisions, we can command a computer to solve incredibly intricate puzzles. Hopefully, this explainer has completely demystified the concept for you, turning what felt like a confusing physical maze into clear, structured logic. And it leaves us with one final thought. Now that you understand how to navigate the maze of every possible solution, what problem are you going to tackle first?